Alright, welcome back everybody. This is the second video on the Approximating Areas with Riemann Sums Part 1 lesson, where we're introducing you to the types of Riemann sums and the trapezoidal rule, and showing you how to do those things algebraically. We're going to pick up where we left off with our first example. We're going to go on to Part D now, and talk about how we use a trapezoidal approximation with 4 subintervals. And if you remember the last video, we found the width of each subinterval by taking the width of the entire interval, which was 10 minus 2 in this case, and dividing by the number of subintervals. And so we want each subinterval to be 2 units wide. Now in all of the RAM estimations, or the Riemann sum estimations that we did in the first video, we chose a single point on the curve to determine the rectangle that we used to approximate the area under the curve, the left endpoint, right endpoint, or the midpoint. In the trapezoidal approximation, we are going to actually use the function value at both ends of the interval. So for the first interval here, we are going to draw a trapezoid like so. And if you do not remember the area of a trapezoid, the area of a trapezoid is 1/2 times the base times the height times the average of the bases. Well, our height here is this distance, 2 units, and our bases are these 2 distances. So the area of this first trapezoid that we're looking at is going to be 2 times the average of the bases, 1/2 times f of 2 plus f of 4. And that's going to be my first trapezoid. My second trapezoid, same idea. It's still the same width, and then the average of the bases, but this time the bases are the value of the function at 4 and the value of the function at 6. And then my next interval from 6 to 8, again, same width, and then the average of the bases. And then my last interval, same deal. Look at how close the trapezoids come to approximating this curve. It's going to be, should be a really good approximation for the value of this. And one thing you'll notice here is I'm calculating the areas of these trapezoids one by one, and we did the same thing with the Riemann sums in the beginning. We can always calculate the areas of these shapes one by one for each subinterval. It's nice when the rectangles or the trapezoids have uniform widths, because when they have uniform widths, we can go ahead and just factor that expression out, and that's what I'm going to do here. And I'm going to write this a little bit differently. Notice that these are uniform, so I can factor out that 2 times 1/2. Of course, that's going to end up being 1 in the end. But then if I look at these other measurements, you see what happens here. I've got f of 2, and then f of 4 appears twice, as the right endpoint of the first trapezoid and the left endpoint of the second. And then f of 6 also appears twice. And then f of 8 also appears twice. But then f of 10 only appears once. So I can shorthand this. I have the left endpoint of the interval, the right endpoint of the interval, and then 2 times the sum of all of the other endpoints of each of the subintervals. So I like to do that when I have uniform widths in the trapezoidal rule. It's not necessarily something that you've got to do. And I think I found the values of f of 2, all of these function values in earlier examples, so I can just go ahead and pull those out. F of 2 was 6.2, f of 10 was 3, f of 4 was 7.8, and f of 6 was 7.8, and f of 8 was 6.2. And so I'm going to have, let's see, 9.2 plus 2 times, and that's 15.6, 21.8. And so that's going to turn into 9.2 plus 43.6. And our approximation using the trapezoidal rule is 52.8. All right. So now, after watching these first two videos, you've seen left Riemann sum, right Riemann sum, midpoint Riemann sum, and trapezoidal sum in context algebraically. Now it's just a matter of you doing a little bit of practice with those and getting good at finding the widths of the subintervals and setting up these calculations. All right. One more thing to talk about in this video. When we have functions that behave in a predictable way, we can state some things about and know some things about whether our approximations are overestimates or underestimates. Okay, let's start with this first scenario. If we have a function that is strictly increasing, okay, it's increasing all the time from left to right, and I've drawn a function that's increasing all the time from left to right. Two things follow from that with our left Riemann sum and our right Riemann sum. We can't necessarily tell anything from whether a function is strictly increasing about the midpoint Riemann sum or the trapezoidal rule, but we can tell something for left Riemann sums and right Riemann sums. Suppose I subdivided this interval up. Let's look at what a left Riemann sum looks like. There's a graph of a left Riemann sum. And let's look at what a right Riemann sum looks like. And what happens here, with the left Riemann sum, all the rectangles are underneath the curve. And so I have all this area here that I'm shading in. That's all area that's under the curve, but that is not counted by the left Riemann sum. And therefore, that's indicative of the fact that the left Riemann sum is an underestimate. And the reason why the left Riemann sum is an underestimate is because for an increasing function, the value at the left endpoint is going to be smaller than all the other points in the interval, and therefore the rectangle is going to be lower than the curve on the entire interval. The opposite happens with the right Riemann sum. The right endpoint on an increasing function is always larger than all the other values of the function on the interval. And so we've got all this area that I've shaded in here that the right Riemann sum is counting, but that is not underneath the curve. And so the right Riemann sum here results in an overestimate. All right, similar idea with functions that are decreasing. The left Riemann sum this time, when we've got a function that's strictly decreasing, left Riemann sum is going to end up being an overestimate this time, because for a decreasing function, the left endpoint is higher than all the other function values in the interval. And so we have all this extra area counted by the rectangles that isn't actually under the curve. And for the right Riemann sum, when the function is decreasing, we have all these gaps. Of area that is not included in our approximate because the value of the function at the right endpoint is smaller than the value of the function anywhere else in the interval. So when we have functions that are strictly increasing and decreasing, we can definitively say 100% whether a Riemann sum that's a left Riemann sum or a right Riemann sum, whether it's an underestimate or an overestimate. And you'll frequently see these kinds of statements, these kinds of questions about these Riemann sum approximations, and you want to know how those work. All right, another scenario where you can tell a good deal about whether the estimate is an overestimate or an underestimate deals with using the trapezoidal rule to find approximations, only this time it doesn't have to do with whether the function is increasing or decreasing, but it has to do with the concavity of the function. And so if I have a function that's concave up, the trapezoidal rule will produce an overestimate. And if I have a function that's concave down, the trapezoidal rule will produce an underestimate. In order to illustrate this, because it gets a little hard to see when the more trapezoids we put under here, I'm just going to go ahead and approximate this using a single trapezoid from one end to the other. There's that single trapezoid. And look at all this area between the trapezoid and the curve that the trapezoidal rule counts, but it actually is not underneath the curve. So here we've got a curve that's concave up, therefore the trapezoidal rule results in an overestimate. Here we've got a curve that's concave down, and the trapezoidal rule results in an underestimate, and we've got all this undercounted area here. Okay, so we've got three scenarios that we can pay attention to as far as whether or not an approximation is an underestimate or an overestimate. If a function is strictly increasing, left Riemann sum will be an underestimate, right Riemann sum will be an overestimate. If a function is strictly decreasing, then the left Riemann sum will be an overestimate, the right Riemann sum will be an underestimate. If a function's concave up, then the trapezoidal rule will result in an overestimate, and if it's concave down, then the trapezoidal rule will result in an underestimate. All right, that's the end of this video and the end of this lesson. Come back next time to see approximating areas with Riemann sums, part 2, where we will talk about using Riemann sums for numerical data instead of algebraic function data like we used it for in this lesson. All right, have a great rest of your day, everybody. See you next time.